This last in a series of three short lectures on bottom processes focuses on the transport of sediment that occurs due to the hydrodynamic forcing. Probably the most important idea about transport is whether or not there is transport, which depends on the relationship between the stress on the bed that comes from waves and currents or their combined interaction, and what we call the critical shear stress of the bed. The critical shear stress is a property of the bed, the sediments. It's the amount of stress that the hydrodynamics must provide in order to mobilize the bed. So basically, if the hydrodynamic shear stress exceeds this value, the bed will be mobile. We can often look at this in terms of what's called a Shields diagram. Now this would be for fairly uniform sediment. There are a lot of difficulties if you're dealing with, for example, cohesive sediments like muds that like to stick to each other, or even non-cohesive sediments, rocks and gravel and sands that might all be together with a wide range of grain size. You tend to have processes such as armoring, where essentially the sand might be available to the flow, but it's hiding among the rocks. So computing this critical shear stress is actually quite difficult. If you have a uniform grain size, you can have pretty dependable formulas. For example, this chart right here, which is based on fairly uniform grains in the bed. Essentially what you look at is your diameter of that fairly uniform grain size. Here, if the diameter of our grain size is, for example, around 0.2 millimeters, so this would be a sand, you can determine that the critical shear stress is roughly 0.1 newtons per meter squared. This is a log-log plot. 0.1 newtons per meter squared. The log-log allows us to have a pretty flat line here. So if the shear stress in the fluid or on the bed is anything above that, exceeding that critical shear stress, then you will have transport. If it is below it, the bed will largely remain static. So there's a threshold of motion. It isn't ramping up from zero. Basically, you have no motion of the bed until you get to this critical value, then you have action of the bed. So it's essentially a very nonlinear process. Again, once we get the bed going, there's a few classes of transport. One is suspended load, and this primarily relates to finer particles, sands or finer, where the sediment can be suspended into the water column. So the turbulent processes in the water column are strong enough to counteract the settling velocity of the sediment and keep it suspended for some duration within the water column. So that sand is going to move with the flow downstream, suspended in the water column. At some point it may contact the bed again, be resuspended again, etc., and move its way downstream, but it's within the water. Bed load is the kind of transport shown in the first video. In the first segment we watched in river flow, it was primarily sheet flow and bed load, where the fairly strong substrates there, they were like little pebbles, were moving along the bed, just rolling and jumping along the bed. So there's two sort of processes there: saltating, where it's getting knocked out of the bed, suspended essentially for an instant, back down in the bed, or just rolling along the top, which is mostly what we saw in that video. So these are bed load, and this is suspended load. There's two types of formulations. Bed load are principally the larger substrates that can't be suspended in the water column due to their very large settling velocities. The suspended refers to sands or finer, for the most part. And again, here's another drawing showing the kind of differences. Saltating, you have these jumping kind of rocks, rolling. It's frequent contact with the bed, and the flux really depends. So flux can be measured. We put a line across there, and we see how much material is moving across that line per unit time. So that's kilogram per meter of length of the line per time, so weight per distance per time, and that's a flux. So it depends on the characteristics of the sediment, the kind of bed stress, and also depends strongly on the slope of the bed. If the bed is sloping significantly, then gravity can play a role and help aid or inhibit the flux, depending upon if the currents are trying to move it up slope or down slope. Suspended load often can be described by something what's called a Rouse profile. you often, and you look at concentration, so here it's grams of solid matter, solid sediment per liter of the fluid. That's a typical value. Grams per liter in the fluid, sometimes grams per kilogram as well, depending upon the nature of the sediment concentration. So this is just a bunch of data points someone took. This is vertical distance from the bed, and you can see if you fit it with a Rouse profile, you get a pretty reasonable thing. So after this, I'll ask you to watch a video I made using the general ocean turbulence model, where I included a sediment model within that, and you'll see that the suspended sediment concentration mimics roughly this Rouse profile. You have very large concentrations nearest to the bed, decreasing away from the bed. So up here, the odds of a particle staying up here when it's trying to settle and turbulence is fighting it are slimmer than down here, where it can be easily drawn up in the water column by the strong turbulence and against the settling velocity here. So this is a suspended load. So again, turbulence is essentially fighting with settling. The particles all want to come down. The turbulence are able to keep them up in the water column. You can have an interaction of the flow with the bed, and you can result in these kind of bed forms. Here you see current generated bed forms. Actually, the flow is moving this way. Current generated bed forms, which have typically a soft slope on the upstream side and a hard slope on the downstream side. They look a bit like a sawtooth. They're asymmetrical. The currents move in one direction. Waves, because they move symmetrically back and forth, don't have a directionality to them. These are the kind, if you go stand at the beach, even a local beach like Mattapoisett, you stand right at the edge of the water and you look down, you'll see these little ripples there. They would be on the order of 3 or 4 centimeters apart, maybe 5 centimeters apart. Very small little ripples in the water. Those are caused by the waves at the water's edge, and you can see them here, that there isn't any real directionality to them. You can also have very large bed forms, such as sand waves. This is San Francisco. You can see this is Alcatraz Island within the bay, so this is outside in the Pacific, and they have these very large sand waves. They have these in the Bay of Fundy as well as Muskegon Channel. So these have wavelengths on the order of hundreds of meters, and they can have amplitude on the order of tens of meters. They have them on Georges Bank as well, and they move slowly, centimeters per day. They're moving and migrating depending upon the residual currents of the system that will sort of determine the direction of travel. These bed forms result from an interaction of the sediment dynamics with the hydrodynamics, all of these. I'll show a brief movie if I can. Is it this one here? So this is a lab study. They're running flow, I think it's from left to right, I can't remember, in this tank. There's lots of students wearing white lab coats, which is kind of weird. And they're running at 400% speed, so you'll see the students move around sort of rapidly, but they're not drugged out or anything. So we have, it looks to be moving left to right. You see the bed forms moving downstream. The fluid's moving over. You have the sharp back side of these things, but none of them are the same. There's no kind of there's some regularity, but they're all different, these waves. They're propagating downstream. And you can have this kind of transport. Here they're referred to as dunes. These are the same things that we see on land or even in deserts. They can build these kind of structures, the interaction there between the wind stress, and the, I'm not sure what that is, and the sediment transport of the desert. Coming back to our lecture, what are some implications on this? This is from a paper I worked on with Brad Harris, a former student of Kevin Stokesbury. And what Brad did was from Kevin's video survey, he was able to derive what the sediment components looked like on the seabed with spatial variation. So essentially they take these quadrats and the pyramid drops to the bottom, and in addition to measuring scallops and enumerating scallops, they actually look at what substrates lie below, and they quantify them in 4 or 5 different categories. And from that you can determine, you can sort of characterize the seabed where the pyramid is dropped. And we work through a number of ways of calculating from that seabed characterization what that implies about the local critical shear stress. So this is a critical shear stress derived from the Stokesbury scallop survey by Brad. This is from FECOM. This is from Chen's Professor Chen's tidal model, and this shows the shear stress, maximum shear stress, from tides, only tides. We're not considering wave-driven processes or wind-driven processes. These are only from tides, and you can see in shallow waters where the currents are stronger, the stresses are higher, and you're getting max on the order of 2 or 3 newtons per meter squared, 2 or 3 pascals in the cap of George's Bank and along Nantucket Shoals. And then what we looked at was the simple ratio of this tidal generated stress to the critical shear stress of the sediment, and that gives you a sense of how mobile is the bed. If tau naught is less than tau critical, then you have blue, and that's the bed is essentially immobile to the tidal flows. If you have a strong red, that means that the shear stress associated with the tides is much greater than the local critical shear stress. And so you sort of see these patterns emerge where there are places even on the cap where you have this cobble and large substrates that are fairly safe in a sense for the scallops, where in the absence of wave-driven stresses you don't have much mobility of the bed, which is pretty interesting. So again, this is coupling a video survey and a oceanographic model. Some other applications thinking about sediment transport from dredging. This is an aerial view. It's a little difficult to see of dredging operations. Here's the ship. And they're dredging, and you can see this, it suspends. It causes sediment to suspend in the water column. It's mostly silt, what you're seeing. And actually, there's pretty cool eddy motions here. I didn't notice this before. Behind these ships, so you have these streaks of sediment. So you're inducing suspension of sediment through a dredging operation. The same thing happens if you, say, bury an electric cable. You're basically pneumatically hitting the soil, putting it in suspension. These are the kind of things when people are permitting things like a wind turbine, they have to be very concerned about. And so let's just have one video to show you that. This is an image of a scallop dredge. I'm sure there are better ones than this, but this is one dragging along the bottom. Theoretically, here it goes. You can see it dragging, and you see the suspension that's occurring. It's also dragging very large, disturbingly large cobble along with it. But this is inducing a disturbance to the seabed, a scouring of the seabed, as well as suspending sediment transport into the water column. Now, key thing is, of course, there are efforts being made to reduce this impact. That's something that Pingguohe's working on and others. But how large is this impact relative to the natural impact? So again, we see waves and currents are also suspending sediments in the water column. So if your fishing impact is tiny compared to the natural impacts, then you can neglect it. If it's not, then you can't neglect it. So that's an important criteria to establish, is what's that relationship. And also the suspended sediment itself, or sediment transport, affects the animals on the bottom. I mentioned in a prior unit that you have one issue is mortality of new settlers. They're quite tiny, maybe the size of a thumbnail, and they're easily buried in the sediments. If you have a big storm event, they can't get themselves out of 3 or 4 centimeters of sand. So larger ones are better able to survive. And also when the flow starts moving and you have this kind of suspended sediment in the water column, what they're eating, they're trying to pull out the actual nutrients from the water column, which may contain a lot of solid materials. So they have a way of filtering out these solid materials, but they can only filter to some degree. So you get typically this kind of domed relationship between clearance rate and flow velocity. So flow velocity going this way and clearance rate, you have a domed relationship. At low flow, you're not able to filter a lot of fluid because it's simply not moving. You have to do the work to suck it through rather than having the water filter through itself. It's some kind of, as you increase the flow velocity, that things improve in terms of your ability to pull cestin out of the water column. But then as the flow velocity gets too high, now you have feeding inhibition. Essentially, you get a lot of suspension of sediments, and it's hard to clear that, and so it's more difficult to feed. So there's typically these kind of speeds at which it's easier to feed, and there's a number of papers by Wildish and others looking at these relationships, albeit many of these were done in tank studies, so it's difficult to duplicate the real environment. The last topic I want to mention is longshore drift. Let me show you a quick video about that. I'll put the link up on the website too if you want to listen to the whole audio on this. This video from Pearson shows the waves are essentially moving obliquely to the land. So here's land, and the waves aren't moving directly on shore or directly parallel to land, they're moving obliquely to land. And that derives a net transport due to waves of sediment along the beach in the direction, in this case the waves are moving obliquely this way, drives a longshore drift in this direction, a net sediment transport due to those waves. Now there's lots of people have to deal with structures. If you look all around here, you see various structures. One of them are these groins. The groins move are set perpendicular to the beach, and essentially what they do is they trap the sediment drift. So I put this in there. They've added sediment drift in. You can see how on the up wave side of these groins, that is on the upward side in terms of longshore current, you can see it traps the sediment and it leaves a net deficit of sediment on the backside. So this is one of the problems with groin, is that in the 50s and 60s people were putting these in all over the place. If you go to the south side of the Cape in Dennis and Harwich, you see a multitude of these, and actually the drift is the same direction. So it's from west to east there. And so someone would install one on their property, on the east end of their property, so they had a nice beach for themselves, but then their neighbor would say, "You stole my beach." So then they would install one, they would install one, etc., etc. And so the race is on, and now we no longer believe we can control nature, so you don't see many installations of such anymore. The second feature we see a lot are breakwaters. These are primarily used to control waves going into a harbor, but also if you extend these far enough out, you get away from where the wave-driven transport is strong, and you can actually prevent infill of sediment into an estuary to keep a navigable channel open. They do the same thing essentially. The net effect is that you'll get trapping on the upstream side and a deficit on the downstream side. I think there's a little image here of an actual jetties, and you can see this is clearly the typical longshore side, and there can be a seasonality to the direction, but here it looks whatever season this is in. This is the upstream side in terms of the longshore transport, so the net waves are moving from left to right on this page, and you can see a deficit on the downstream side, and obviously they've designed this maybe to take that into account. And the last one are interesting, these kind of idea, these offshore breakwaters, and these have different names in different countries, but again, what net effect is the waves are moving in, but you have some diffraction around these of the waves, but you have a weakening of the wave state here. So the waves are strong, they don't have any breakwater influence here or here, but in the middle you have a weakening of the wave state, and it tends to truncate or slow the longshore drift, allowing sediment to build up here. I think that's shown in this, yes it is, in this video. See that it slows the longshore drift. You have net deposition here, net erosion here. This is kind of an interesting effect because this is the same effect that happens behind wave energy generators. The wave energy generator is pulling out the wave energy, and so you'll have a net deposition occurring behind them. And it's one of the concerns if you start modifying, doing a lot of nearshore work, what will happen to the nearshore transport due to these wave energy generators? It's a pretty neat thought. Okay, I'm going to take you back to our little lecture. Oops, wrong video. 1 second. No, that ain't it. Okay, here. Okay, so back to longshore drift. There's a great little report on longshore sediment transport done by Woods Hole Sea Grant and the Cape Cod Cooperative Extension. And basically what they did, I believe, is they took an aerial photograph. They looked at all the groins and structures on the Cape, and from them they were able to deduce which way the longshore drift was going. There's a bunch of different studies, 34, 64, all the way to 93, and you can see these patterns. So pick, for example, 79, which seems, or 66, which is pretty comprehensive. You see on the bay side of the Cape, you have largely the longshore drift is to the east, with the exception of this area around the entrance to Barnstable Harbor. It's to the east here, along the bay beaches in Brewster. In this part of the bay, the Cape here, we have a divergence here and around this area on the entrance to Wellfleet Harbor. Around Great Neck here in Wellfleet, you have this southward transport of the longshore drift, and you can see it, how this kind of structure here would maintain itself against erosion coming from the onshore waves. You have these longshore drift. Again, you have a node here where you have divergence. You have longshore this way, and this way means a net erosion's occurring somewhere in this vicinity of the inlet here in Truro, I guess. And you have a net convergence again in Provincetown, where you have the net longshore flux is moving this way here and this way here, allowing you to maintain this sort of pronounced point. You also have a divergence in the backside of the Cape here, and the net accumulation down here in Monomoy. So I think this is sort of a fantastic little diagram. There's some disagreement between years, which is what's circled here in the red things, but this is, I believe, is deduced from looking at aerial surveys. So what you can do as an exercise is essentially take Google Maps. I would advise zooming in down here to Harwich. You'll see lots of little groins in Google Maps, and you can look at those groins and deduce which way the longshore drift is going, at least when that photo is taken, by the snapshot, by the determining which side has sand accumulation and which side has net erosion. Again, there's a seasonality to this. The summer experience a lot of southwest winds in Nantucket Sound, which would produce this longshore drift in this direction. The winter out here has quite variable. So the southwest winds in the summer are offshore here, but you have onshore winds from a northeaster, for example, very strong onshore winds. But a northwest wind would produce very limited longshore transport. So, but there's a seasonality to that. Okay, that's it.